So let's talk about bit vectors. Bit vectors are a kind of very simple data structure that we've used elsewhere. So for example, you may have seen Bloom filters, and Bloom filters are an example of a data structure that really just consists of a bit vector. It consists of an array of bits that are either set, equal to 1, or unset, equal to 0. And in the case of Bloom filters, we're using the bit vector to represent an approximate version of a set. If you're not familiar with Bloom filters, that's not important. In this particular case, the case of a Bloom filter, the bits in the bit vector and where exactly they are in the bit vector are not particularly meaningful, right? There's not a very strong, if you see the bit at offset 8 is set, that doesn't really tell you anything in particular about the set. But we're going to be thinking about bit vectors where there is some meaning to each of the slots in the bit vector. And when the slots have meaning, there are reasons why we might want to query and navigate the bit vector in a lot of different ways. Right? So if the slots have meaning, then there's something meaningful to, for example, jumping from set bit to set bit in the bit vector, or trying to figure out the distance between two set bits in the bit vector, or trying to find the first set bit or the last set bit, things like this. There is going to be a particular reason why a particular bit lives in a particular slot of this bit vector. Okay, so let me show you a bit vector and ask the question, does this bit vector have some kind of meaning? Is there some significance to which of the bits are set? Well, that's a question that requires probably that you look at this for a long time and try to figure out what pattern, if any, you're seeing. That'll take a while. So let me give you a hint, which is, let's say this is a bit vector we're using in a program that we're writing, and its variable name is prime. Okay, all right, that's a good hint. So let's look at that bit vector a little bit more closely. What if I were to write numbers next to each of the slots of the bit vector? Okay, we start to see a pattern emerging, which is that the set bits, the bits that are set to 1 in this bit vector, correspond to primes, right? 2, 3, 5, 7, 11, 13. Okay, so that's the meaning of this bit vector, is that the offsets correspond to numbers, and whether they're set or not corresponds to whether they're prime. So how might we go about querying this bit vector? What are some of the questions we might want to ask? Well, in some situations we sometimes we would like to figure out, we have a number and we'd like to figure out what's the next highest prime. If I have some number, in fact, this is useful for universal hashing, right? When we want to figure out how should I set p, the size of my prime field, I'd like to know, well, what's the size of my universe? I'd like to pick something that's slightly larger than the size of my universe. So I might be asking one of these, what's the next highest prime type questions. Well, phrased in terms of this bit vector, it's like saying, what's the next highest set bit? I'm at a particular offset in the bit vector. What's the next highest set bit? So that's one example of how we might be querying a bit vector in order to get the answer to a practical question. Here's another example. Let's go back and actually use the Bloom filter as an example. What if we really did have a bit vector that represented a Bloom filter? Well, we just said before there's not a particular meaning to the slots of a bit vector that's representing a Bloom filter. Just by looking at the pattern of zeros and ones, we can't figure out which items are in the input set, for example. But we can figure out something about the cardinality of the set, how many items are in the set, by looking at the spacing between the set bits, right? If the set bits are spaced very far apart, that's a hint that the set is not very big. If the set bits are actually packed in quite densely, that's a hint that the set is big. So we might still want to navigate the bit vector, but we'd be asking questions like, how far is the distance between consecutive set bits, adjacent, the next set bit over? On average, how far do I have to go to the next set bit to the right, for example? Okay, so maybe there is some reason to query and navigate a bit vector when it's representing a set, as in when we're using a Bloom filter. Another situation is we might have a bit vector that represents not an approximate set, but a set, where every element of the universe is one of the slots in the bit vector, and that slot is set to 0 or 1 according to whether that element from the universe is present in the set or not. This might be, for example, if we're in a situation where the vocabulary is rather limited, and we'd like to be able to compare large documents to figure out if the documents have similar meaning, well, then we might just want to compare them based on whether they have similar bit sets, right? So that'd be another example where a bit vector is representing a set, and we might want to navigate it in much the same way, query or navigate it in much the same way that we wanted to query or navigate the Bloom filter. Maybe our set bits are representing characters, not just zeros and ones, but maybe the zeros and ones are standing in for symbols from a larger alphabet, like the DNA alphabet. So for example, this figure here is showing a one-hot encoding. That's just a particular way of taking characters from a larger alphabet and encoding them using actually several bit vectors. You know, one bit vector for every possible symbol in the alphabet. In that case, navigating the bit vectors is a bit like jumping around from character to character. We could do things like visit all the A's in the DNA sequence, or visit all the G's in the DNA sequence, or maybe put them together. So we've thought of different things that the bit vectors might be, kinds of things that the bit vectors might be representing, and different queries we might want to do with those bit vectors. Can we break it down so that all these different queries or things, navigations we might want to make through the bit vector are really just built on a few simple ideas? And so that's the motivation for talking about a particular set of 3 bit vector queries, the so-called RSA queries, or rank select access queries, which it turns out you can put together in various combinations to get more sophisticated queries. So even though we could just off the top of our heads think of a very wide variety of possible queries we might want to do, you know, get me the first set bit, give me the last set bit, give me the set bit in the middle, jump from one set bit to the next going down, from one set bit to the next going up. You know, we could think of a lot of varieties, but the good news is that they tend to all boil down to just a few relatively simple queries, namely these 3. Okay, great. So let's study them. Rank, select, and access. And even though it's listed third, we're going to do access first because that's the simplest one. What does access do? It simply returns the value stored in the bit vector at the given offset. So if we're asking an access question, we give an offset I, and the query returns whether the bit at offset I is set or not. Okay? So pretty simple. It's certainly conceptually easy. The only reason why access might start to get hard is if we were to consider compressing the bit vector. Right? So the bit vector might be extremely redundant, and we might be able to come up with a clever way of storing that bit vector in much less space, but that might complicate then the question of how do I get the bit that was at a particular offset with respect to the original uncompressed array. Right? There might be a sort of level of translation that needs to happen, but that's not a concern that we have right now. We're only going to deal with uncompressed bit vectors. But that's the only reason why maybe the access query could get a little bit hard. Well, maybe one more caveat here, which is that when we talk about accessing bits, we're sort of assuming that the computer has a good way. If we tell it, give me the bit at offset 1,400,000, we're sort of assuming that the computer has a good way of getting at a single bit in an operation like that. Whereas in practice, computers are much better at accessing chunks, you know, what you might call a machine word. And so there might have to be a little bit of translation that needs to happen because a given bit might actually be treated by the computer as an offset within a word, and therefore you have to address the word and then address the bit within the word. Not a major concern here for us, though. A notational point that's important is when we think about offsets within the bit vector, we think about the different slots within the bit vector, starting from the top down, let's say. We're going to do our indexing starting at 0. Okay, so let's look at the answer to the access query for a couple of offsets. So b dot access of at 2, at offset 2, equals, we just have to count down from the top starting at 0. 0, 1, 2 is 1. And let's do b dot access 7. So same thing, we just have to count down from the top. 0, 1, 2, 3, 4, 5, 6, 7, and we get the 0 at that offset. Okay, that was access. Let's look at rank. Rank's a little more complicated. So the way rank is defined, and it's important to note that rank has a subscript. Okay, so we see a subscript of 1 here and a subscript of 0 here. Let's ignore this second line for now and just concentrate up here on rank with a subscript of 1. Rank with a subscript of 1 equals the sum from j equals 0 up to I minus 1 of b of j. What's b of j? Well, that's just accessing the bit at offset j. So rank sub 1 of I is adding up all of the 1s that it sees in the bit vector up to, but not including, offset I, right? So this is an important caveat here, is that for rank sub 1, we're counting the number of 1s up to, but not including, if there's a 1 at offset I. Okay, and then going back to the second version of rank, where the subscript can be 0, rank sub 0, I'll call it, subscript 0, this is basically adding up the zeros instead of adding up the 1s. It's adding up the number of zeros up to, but not including, offset I. Or another way to say this is it's just I minus the rank sub 1 up to offset I, right? We're just saying if it wasn't a 1, then it was a 0. So I know that if I just do I minus the rank sub 1 query up to I get the answer for the zeros rather than for the 1s. Okay. Let's do a couple of rank queries, make sure we understand this. It's going to involve visually scanning along this bit vector and adding up how many 1s we see or adding up how many zeros we see, depending on which version of the query we're doing. Okay, so let's do b dot rank subscript 1 at offset 2. Okay, so what do I have to do? I have to count the number of 1s up to, but not including, offset 2. So if we do that, we see, okay, we start at offset 0. That's not a 1. Go to offset 1. That is a 1. So we have to add 1 to our total so far. And then it's up to, but not including this offset. So we are not going to add this 1. It's just going to be 1. The answer is 1. Okay? So let's do another rank. This time it's important to notice that we're doing the rank sub 0. It's the rank subscript 0. So we're doing rank subscript 0 at offset 5. What do? We have to add up all the zeros we see up to, but not including, offset 5. So starting at offset 0, 1, offset 1, offset 2, offset 3, 2, offset 4. Okay, and then we don't go on to offset 5. It's up to, but not including, offset 5. So what did we see? We saw 2 zeros. Okay, so the answer to that is 2. Let's do one more. So let's do the rank sub 1, subscript 1, at 8. All right, now I have to look at all these elements and count up how many 1s I see. 1, 2, 3, 4, right? Okay, so the answer to this is 4. That is rank. It's counting how many times either 0 or 1 occurs up to, but not including, the given offset. All right, that's 2 out of 3. Let's look at the third query, which is called select. Select is defined in terms of rank. So again, select is going to have a subscript, and I'm just now showing you only the formula for subscript 1, select sub 1. So select sub 1 of I is what? It's the maximum j such that the rank sub 1 at offset j equals I. Okay, a simpler way of saying this is that select sub 1 of I is saying, please tell me the offset of the ith 1 bit. Okay, so let's just show the select sub-zero counterpart to this one. What's different about this? Well, now I've got select sub-zero. It's just using the rank sub-zero instead of the rank sub-1. So it's the rank sub-zero counterpart to what we just said. So again, to say the shorthand version of it, select sub-zero of I is saying, give me the offset of the ith 0 bit in the bit vector. Okay? And don't forget that the rank counts up to but not including the given offset. Okay, so let's do an example. Let's do an example. Okay, so let's do an example. Here's b.select sub1 of 0. Okay, so again, what is this query defined as in terms of rank? So let's go look over here. It's the maximum j such that b.rank sub1 at j equals I. Okay, and the I in this case is 0. So let's do this. Let's let our j start at the beginning of the bit vector. Then let's ask, what is the rank sub1 at that j? And just keep going down. Okay, so what's the rank sub1 at j equals 0? Well, it's 0. Okay, so far this condition is satisfied, but I'm trying to find the maximum j at which that condition is satisfied. So let me keep going and try j equals 1. Okay, what's the rank sub1 at j at this row? It's still 0. Okay, because there's no I would only count this position if it were a 1, but it's not a 1. So the rank sub1 at offset 1 is 0. Now let's try offset 2. The rank sub1 at offset 2 is 1. So now I know what's the maximum j such that b.rank sub1 of j equals I. It's 1. Right? After 1, it becomes 1. It becomes higher than 0. Okay? So again, like we said, maybe it's better to use the shorthand version. The shorthand is just that b.select sub1 of 0 is saying, please give me the 0th first, the offset of the 0th 1 bit, right, which is 1. Let's use that shorthand. We'll use that shorthand definition for the next couple of examples. Okay, so select sub-0 of 3. That's saying, give me the offset of the 0, the 4th 0, or the 0 of rank 3. Okay, so in other words, I need to count 4 zeros down and ask what offset is that. All right, so let's do that. So 1, 2, 3, 4. It's this one. So what offset is that? Let's do that again. 0, 1, 2, 3, 4, 5, 6, 7. That's at offset 7. Okay, so b.select sub-0 of 3 is 7. Let's do one more. Select sub1 of 5. All right, so I'd like to know the 6th or the 6th set bit or the set bit of rank 5. So let's look for that. 0, 1, 2, 3, 4, 5. Oh, it's all the way down at the bottom. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's at offset 12. Okay? All right. So let's think about these. So we've got our 3 queries now. We've got rank, we've got select, we've got access. Access is just saying, give me the value at a given offset. Rank is saying, how many positions of my bit vector is equal to some value up to a certain position. Select is doing the reverse. It's saying, what is the offset that contains the 1 or 0 of a particular rank? Okay? You get the impression that rank and select are kind of undoing each other in a way, that they are not quite, but they're sort of like inverses of each other. Rank is taking a offset and it's giving you back a rank. How many of something is there up to that offset? Select is taking a rank and it's giving you back an offset. Okay, so there's a relationship between the two. So let's think more about what are the domains and ranges of these 3 kinds of queries. All right, so here are my 3 kinds of queries: access, rank, select. Let's just, by way of terminology, let's let the length of the bit vector be n, and let's let m equal the number of set bits. So we're going to assume for now we're talking about rank sub 1 and select sub 1. We're concerned with the queries that have to do with the bits that are equal to 1. And there are m such bits in the bit vector. Okay, so here's my picture. I've got 3 sets here. The set of 0 up to n, 0 up to m, non-inclusive, and the set of just 0 and 1. And so now let's think about what are the domains and ranges of these 3 kinds of queries. So b.access is saying, give me an offset into the bit array. Okay, which one of these sets represents offsets into the bit array? Well, that's this one, right? The bit array has length n. So this is the set that represents offsets into that bit vector. Tell me what is the value of a bit at a certain position. Well, that's just 0 or 1, right? So the range of that function, of that query, is this set here. So access takes a value from here and returns a value from here. Okay? So there's access. Now let's think about rank. Rank is you give me an offset, and I'll tell you how many set bits there are up to but not including that offset. So the input to the function is a offset. So again, that's this set, right? 0 up to n. And the output is a rank. Aha! Now we can use m, right? Because we said that m is the number of set bits, right? So a rank query is never going to return an answer that's greater than the number of set bits in the array. Right? So the range of the rank query is now this pink set here. So rank is going to go from here to here. Its domain is this. Its range is this. Okay? All right, now let's do select. Select takes a rank and gives an offset. So it's doing the reverse of what we just did with rank. So select is going to have this as its domain and this as its range. So let's draw and select. Okay. Here's an exercise. Now that we've got these basic queries, let's see if we can put them together to make a somewhat more complicated query. So let me propose a more complicated query that's made up of rank and select. And let's see if we can figure out what's the meaning, what's the purpose of this new query? What does it actually do? All right, so here's our query. b.select sub 1 of b.rank sub 1 of I minus 1. Okay, so we're going to do a rank query first, get an answer, subtract 1, and then do a select query. All right, so let's work by example. Let's just try a couple of examples of what we would actually get. So let's start with the example where I equals 2. Okay, so the first thing we want to do is this inner rank. So what's the rank sub 1 at 2? Well, that's just the number of 1s up to but not including offset 2. So 1. There's 1. 1 such 1. So the answer to that is 1. Next thing we do is we're going to subtract this 1. So we get 0. Then that becomes the argument to this select query. So now we're doing select sub 1 of 0. In other words, give me the 0th 1 bit, the 1 bit of rank 0. Well, that's this one, right? The one at offset 1. So the answer to the overall query is 1. Okay, so we put in 1, got back 1. Let's do another query. Let's do another, you pick a different value for I, in other words. Let's try I equals 8. Okay, so again, let's start with the inner rank. We're doing the rank sub 1 at offset 8. So let's count how many set bits there are up to but not including offset 8. 1, 2, 3, 4. So the answer to that rank query is 4. Now we have to do this minus 1. We get 3. The 3 becomes the argument to the select query. So let's select the 1 of rank 3. 0, 1, 2, 3. So it's this one here, and that's at offset 0, 1, 2, 3, 4, 5, 6. So the answer to the overall query is going to be 6. Okay. Let's just look at those two examples, and let's see if we can figure out what they're doing. Okay, so the first example took 1 as its input, and then returned 1. And the second took 8 as its input. Let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8. Took 8 as its input, and it returned 6. Okay, 6. And that final answer was the result of a select query. It's like the select query is, in this case we went right back to 1. In this case we went up to 6. It's like what it's saying is, give me the next set bit earlier. Give me the next set bit earlier. At this position or earlier. Give me the next set bit at this position or earlier. Okay? It's what's sometimes called a predecessor query, or it's a version of a predecessor query. So give me the offset of the next earliest set bit, which might be at the same position. Okay? All right, so that's a good example of something that we already said before has some utility. Like maybe we want to jump from set bit to set bit because we want to know how many spaces there are between them so that we can do a cardinality estimate, for example. Okay, there are a lot of reasons why we might want to do these so-called predecessor queries. That's just one example. Now let's turn to the question of, now that we have our primitive queries and we have some confidence that there's a reason to put them together to make more complicated queries, how would we implement rank and select? How do we implement these queries? Okay, access is, like we said, simple, and it doesn't really get complex unless we do something like compress the bit vector. But how do we implement rank and select? Let's think about it. So my first idea is that we could do what we've been doing so far visually, as we've been just sort of going, scanning down the bit vector visually and counting up what we see, or hopping to the bit that we're looking for. That's just a linear scan, right? So idea 0, I'm calling it idea 0 because it's not very practical, but idea 0 would be, let's just do the linear scan that we've been doing manually, visually, while trying to come up with the answers to the queries so far. So in the case of a rank, we'd be counting, right? We go from the top down and count how many times we see a 1, in the case of rank sub 1. For select, we would be going down and scanning until we get to the 1 of a certain rank. Either way, we can accomplish the query just by scanning and doing a tiny little bit of bookkeeping to figure out when to stop, or what the answer so far is. Okay, so that's idea 0, but it's not practical. We don't want to do linear scans over bit vectors because the bit vectors might be just incredibly large, right? If the bit vector is representing a set in a dense way, right, not an approximate set, but the full set, that could be an incredibly long bit vector. We could be very much not wanting to do any linear scans whatsoever. So let's see if we can be more efficient. So if this idea was very inefficient from a time perspective, let's now look at an idea that's very inefficient from a space perspective, which is that we could simply pre-calculate all the answers, right? So if we're going to do rank queries and select queries, well, we can pre-calculate the answers to all the rank queries and put them in an array called R sub 1 for rank sub 1. These are the answers to all the rank sub 1 queries. And then we could have an array S sub 1 for the answers to all the select queries. And then we have to go fill them in. So what would we do? Okay, rank sub 1. So the rank sub 1 at 0 is 0. Rank sub 1 at 1 is 0. Rank sub 1 at 2 is also 0. Rank sub 1 at 3 is now 1. And now it's 2, 2, 3. You get the idea. We could fill this whole thing in with all the answers. And we could likewise do that with the select. This will actually just reiterate the primes back to us. Okay, so we can just fill those in. And then every time we have a rank or a select query, we just do a direct lookup, right? We go to a particular offset that's just given by the parameter to the rank or select query, look up the answer. But this takes a lot of bits, right? So how many bits does it take? Well, we've got our R sub 1 array here. It has how many elements? Well, it's got n elements. And each of them is a rank. And ranks can go up to however many ones there are, which is m. Right? So we're storing n things. And for each one, we have to store a rank for which we need log of m bits. Okay? So that's what gets me this part, right? The n log m. Now let's look at this select array. how many items are there in the select array? Well, there are as many items in the select array as there are set bits. So there are m of them. And how much space do we need to store one offset into the bit vector, which is the answer of the select query? Well, log of n. So that accounts for this first term that I've put inside this big O. Okay, so overall, the big O is m log n plus n log m. All right, well, so that's a lot of space. Let's just think about how much space and time we're using with this idea. Well, the good news is across the board, access, rank, and select are essentially lookups. Direct addressing lookups, the simplest thing we could hope for. They're all constant time. There's no dependence on n or m with respect to how much time it takes to answer those queries. The access query, well, what do we need in order to answer the access query? We just need the bit vector itself, so we need n bits. And then what do we do with that bit vector? We just look up the bit at a certain offset. It's easy, unless we use compression. Right? So now what's the space requirement for rank? Okay, well that's the one where we had to pre-calculate n possible answers to queries, and each of them returned a rank, so we needed log of m bits for each. So that was the m log n one. Okay, n log m one. So that is just the space we need to store the pre-calculated r sub 1 array. Okay, let's go to the s sub 1 array for select. Well, that's the one where we had as many elements as there were set bits, so that was m, and each one had to point to an offset with respect to the bit vector, so we needed log of n bits to do this. So this is the big O of m log n array. Okay, so that's big. I mean, the amount of space that we need to answer the access query, which is just n bits, is pretty small compared to the amount of space we need to answer these queries, right? We've now got multiplicative log of something factors. Okay, so we'd like to be able to do it in less space. So here's my first suggestion for how we can do it in less space. And it's actually a fairly practical suggestion if your bit vector is very sparse. The suggestion is, here again is the picture with our r sub 1 and s sub 1 arrays. I would suggest let's just get rid of the r sub 1 array and just keep the s sub 1 array. Okay, so if we have just the s sub 1 array, we of course know how to answer select queries, just like before. It's a direct lookup. But now how do we answer the rank queries? Well, that's interesting, because what are the rank queries asking? It's saying up to a given offset, how many set bits are before? So let's just say, for example, that I was asking up to offset 6. Let's say I was asking what's the rank sub 1 at 6. Well, the S1 array is actually telling us something about the answer to that question, because where's offset 6 with respect to the offsets that are in this array? Well, it's in between these two. So what does that tell us? It tells us that these 3 elements are 3 set bits that come before that position. So we actually know the rank. Just by figuring out where 6 belongs in this order, we know how many set bits there are before. And so we can answer the rank query. In other words, to actually do it efficiently, we would do binary search. To actually do this efficiently, we would do binary search on the S1 array. So we would take that argument to the rank query, I. We would use I and do a binary search on S sub 1. And however far into the array we landed, that tells us how many set bits are prior. It tells us the answer to our query. Okay? So now we can get away with just the number of bits we need to store the S sub 1 array, which is m log n. What we've given up is that in order to answer that rank query, we now have to do a binary search, which means we've got a log m factor in the time required to do the rank query. Okay? But that might not be that bad, right? If m is small, in other words, if the number of set bits is low, if the bit vector is very sparse. So this could be a good trade. And indeed, this is a pretty practical way to do it, and a lot of techniques do it this way. So in this regime, we've now changed what we need to write in the rank row of this table, right? So the time of the rank is now the time required to do that binary search on the select array, which is log of m. The space is now the space required to store the s sub 1 array, which we said was m log n. And the note that I have here is that the way we actually satisfy the query is by doing binary search on s sub 1. Okay? Select is the same as before. And we should note that even though I've written out this big O twice, that's the same array in both cases, right? We're reusing the same array to answer the select and the rank queries. So, having discussed all that, we can wonder if we could do even better. And in particular, we can wonder whether we can get in under the number of bits that we need to satisfy the access query, this n bits. Can we get in under that? In other words, is this kind of thing possible? In other words, is this kind of thing possible? Where all the queries take constant time. We would love that. That was what we got from idea number 1, right, where we actually pre-calculated all the answers. We still want access to take n bits, as always. But what we would like is for rank and select to take little o of n bits. In other words, asymptotically growing slower than n, sublinearly in n number of bits. Could we do that? Because if we could do that, we could argue, well, these bit vectors aren't adding very much to the overall amount of space we need. We've got the bit vector, which is n bits. We're not throwing that away. We only need little o of n additional bits in order to perform constant time rank and select queries. Is this possible? And the answer is yes, and we can see how to do it for both rank and select. We'll take them separately because they both take a little bit of time to see. But the answer will be yes, we can do that, but we'll have to see later exactly how.